Hello viewers, today in this program we will discuss graphical method of solution of linear programming problem. Previously we have discussed the formulation of linear programming problem. The graphical method of solution of linear programming problem is very important in business mathematics. It gives the maximum or minimum value of z, that is the optimization of linear programming problem. Linear programming problems with two decision variable can be solved by graphical method. The graphical method provides a pictorial representation of the solution process. In this method, we trace all the linear equalities and inequalities of the constraints to find feasible region of solution. The graphical method of solution of linear programming problem consists of following steps. First, represents the given linear programming problem in mathematical form. Second, draw x and y axis, the non-negative restrictions x greater than equal to 0 and y greater than equal to 0 imply that feasible region lies only in the first quadrant as shown in figures. Step 3, plot each of the constant on the graph as 2x plus 4y less than equal to 16 and 6x plus 2y less than equal to 20. Here in these pictures, the blue line represents the equation and the arrow represents the less than sign here. In the step 4, we identify the feasible region that satisfy all the constraint. Here the yellow area represents the feasible region which satisfy all the constraint above x axis, that is y greater than 0, towards the right of y axis, that is x greater than 0, below the yellow line, that is first constraint less than, and below the blue line, that is second constraint less than type. Step 5, use profit or cost function line approach. Here we plot the line of objective function with z is equal to 0. Start moving the line towards right parallel to itself to get optimum point of feasible region. Here in the picture, the dotted line represents the objective function with z is equal to 0. If we move this line towards B, we find the extremum value at the corner of the feasible region, which is yellow shaded region. Step 6, as an alternative of step 5, use extreme point enumeration approach. For this, we find the coordinate of the corner point of feasible region. Find the value of objective function at each corner point. The point at which objective function is maximum or minimum is the optimal point, and its coordinate give the optimum solution. This is the alternative method of finding optimum value of z, because the optimum solution lies on the corner of the feasible region. We find the value of objective function at all the corners. Now I am going to explain you the process of solution of graphical method with examples. First example here is solve the linear programming problem which maximize z is equal to 3x plus 5y subject to constraints 2x plus 4y less than equal to 16, 6x plus 2y less than equal to 20, xy greater than equal to 0. Its solution is, plot the following inequalities on the graph. We here plot x greater than equal to 0, y greater than equal to 0, 2x plus 4y less than equal to 16, 6x plus 2y less than equal to 20, and find the feasible region. The feasible region is as shown in the picture. The yellow shaded part in this picture, we have plotted here all the constant x greater than 0, y greater than 0, which provide the solution in first quadrant, and then yellow line and blue line are two constants which gives the less than inequalities. The optimum solution lies on any of the corner point of feasible solution. Therefore, we find value of objective function at these corners. The corners are O 0 0, A 6.3, 0, B 2.4, 2.8, C 0, 4. The value of objective function z at these points are z o 3 into 0 plus 5 into 0, that is 0, z a 3 into 6.3 plus 5 into 0, z b 3 into 2.4 plus 5 into 2.8, that is 21.2, z c 3 into 0 plus 5 into 4, that is 20. The maximum value of z is at b. Therefore, optimum solution is x is equal to 2.4 at and y is equal to 2.8, and the maximum value of z is 21.2. Here in this method, we have obtained the feasible region and we have obtained the value of z at all the corners of the feasible region. The maximum value is at one point, and the value of x and y and the maximum value of z are given at this point. Now, we will discuss another example. Example 2, solve the linear programming problem which minimize z is equal to x plus 2y subject to condition 4x plus 6y greater than equal to 2400, x plus y greater than equal to 500, 8x plus 2y greater than equal to 1600, x y greater than equal to 0. Its solution is, we draw the inequalities of all the constants on the graph as shown here. Optimum solution lies on any of the corner point of the feasible region A, B, C, D. Here the A, B, C, D are the points of intersection of these inequalities. A here is on x axis and white line constant, B here is the intersection of white line and blue line constant, and C is here at intersection of blue line and sky line intersection, and D point is here on vertical line and sky line intersection. This arrow shows the whole feasible region which is bounded at A, B, C, D. Therefore, we find the value of objective function at these corners. The corners are A 600 0, B 300 200, C 100 400, D 0 800. Value of z at these corners as follows: z a is 600, z b 700, z c 900, z d 1600. The minimum value of z is at a 600 0. Therefore, optimum solution is x is equal to 600, y is equal to 0. Total minimum cost is 600. Now, we will discuss example 3. Maximize z is equal to minus x plus 2y subject to minus x plus 3y less than equal to 10, x plus y less than equal to 6, x minus y less than equal to 2, x y greater than equal to 0. Its solution: the solution space satisfying the given constant and meeting the non-negativity restrictions x greater than 0 and y greater than equal to 0 is shown in shaded region. Any point in this shaded region is the feasible solution of given problem. Here in this picture, yellow shaded area satisfy all the conditions given in the question, like minus x plus 3y less than equal to 10, x minus y less than equal to 2, x plus y less than equal to 6. The feasible region OABCD gives the solution. The maximum value of z at any of the corner of this region, we find the value of objective function at these corners. The 6 vertices of the convex polygon OABCD are O00, A0 10 by 3, B 2 4, C 4 2, D 2 0. The value of objective function z is equal to 2x plus y at these vertices are z at O 0, z at A 20 upon 3, z at B 6, z at C 0, z at D minus 2. Since the minimum value of z is minus 2, which occurs at the vertex D 2 0, the solution of the given problem is x is equal to 2, y is equal to 0 and z minimum is minus 2. Now, we will discuss some other type of problem. Example 4, solve the LPP, maximize z is equal to 3x plus 4y subject to 5x plus 4y less than equal to 200, 3x plus 5y less than equal to 150, 5x plus 4y greater than equal to 100, 8x plus 4y greater than equal to 80, x y greater than equal to 0. Its solution is the solution space satisfying the given constant and meeting the non-negative restriction x greater than 0 and y greater than 0 is shown in shaded area in the graph. Here in this graph, the colored line represents the restrictions and the feasible region A, B, C, D gives the solution. The dotted line represents the objective function at z is equal to 0. We move this parallel to itself and find the maximum value of z at D. This region is feasible solution. The coordinates of the vertices of the region A, B, C, D, E are A 20 0, B 0 25, C 0 30, D 400 upon 13, 150 upon 13, E 40 0. Value of objective function z is equal to 3x plus 4y at these vertices are z at A 60, z at B 100, z at C 120, z at D 1800 upon 13, z at E 120. Since the maximum value of z is 1800 upon 13 at D, therefore, the solution of linear programming problem is x is equal to 400 upon 13, y is equal to 150 upon 13 and the maximum value of z is 1800 upon 13. Now, we discuss another type of problem, example 5, which maximize z is equal to 5x plus 4y subject to x minus 2y less than equal to 1, x plus 2y greater than equal to 3, xy greater than equal to 0. The solution space satisfying the given constraints and meeting the non-negative restrictions x greater than equal to 0 and y greater than equal to 0 is shown in shaded region of the graph. In this diagram, feasible region is yellow shaded area. Its corner points are A and B, but it is unbounded towards the upward direction. If we take the objective function as dotted line at z is equal to 0, start from origin and move parallel to itself, but there is unbounded region. So, there is no corner point gives the maximum value of z bounded. The objective function when z is equal to 0 is 5x plus 4y is equal to 0. which is shown by dotted line passing through the origin. As z increases, the line moves to right parallel to itself to maximize z, but the region is unbounded. Therefore, it is not possible to get a corner of the feasible region to get maximum of z. Therefore, this LPP has unbounded solution. Now, we discuss another type of problem. Example 6. Maximize z is equal to 3x plus 4y subject to x minus y greater than equal to 0, 5x minus 2y less than equal to minus 6, xy greater than equal to 0. Solution. The solution space satisfying the given constraint is shown in the shaded area. Here in this figure, the two constraints intersect at a point and the inequality gives the feasible region yellow shaded area, but no point of this region satisfying the non-negativity restrictions x greater than equal to 0 and y greater than equal to 0. Therefore, this LPP does not possess a feasible solution. In this figure, the two inequalities represented by 5x minus 2y less than equal to minus 6 and x minus y greater than equal to 0, these two are in opposite direction. Therefore, there is no feasible region which gives in the positive quadrant, that is non-negativity restriction. So, this LPP does not possess a feasible solution. Hello viewers, today in this program we have discussed graphical solution of linear programming problem. Here in this program we have discussed various types of linear programming problem and its solution graphically. Some are less than type of, some are greater than type of, some are mixed type of, some are unbounded, and some problems are having no feasible region. At the end of this program, we have discussed the problem in which there is no feasible region which satisfy all the restrictions. So, we have discussed variety of linear programming problem in this program and its solution graphically. Hope you must have enjoyed this lecture. Thank you.